Hopefully you guys can hear me. Um, let's see, can you hear me? Yeah, you should be able to. But yeah, welcome to the stream. Yeah, I don't expect to get any viewers, but I'm really just doing this so I can hold myself more accountable. But yeah, so whatever. So today we're gonna tackle some neat code. I've done quite a few already, and I want to try to complete this whole list since I'm pretty bad at it, to be fair. Um, But yeah, let's go. We're gonna start with binary search. So the way I do things is like I try to what's it called? I understand the topic first. So if it's like stack, I understand stacks and stuff, and if it's binary search, I'll understand that. And then once I understand that, then I tackle these problems or I try my best to do it. And if I can't do it or I get stuck after like I'll say 15, 20 minutes, I look at the solution and I try it again the next day. All right, so let's get into it. So let's try to understand binary search. So let me just copy this topic. Let's see. Give me this. What was I gonna do? Let's go into Open VS Code so you guys can kind of see. Let's just open this. Which one do I want? Let's open prep. Let's open. I want to open the dictionary, but it's not opening. Okay, let's just open up toolbox. Just did something by mistake. Alright, here we go. So I have this toolbox over here. Let's create one called binary search dot do Swift. How do I see that? This will be the most boring stream anyone ever watches, but it's fine, honestly. Let me just make sure I'm streaming on my. Ooh, I'm not streaming. Am I streaming? Let's see. Can you hear me? Yeah, you should be able to. Am I still streaming? See, can you hear me? Yeah, you should be able to. Am I still streaming? See, can you hear me? Yeah, you should be able to. I don't even know if I'm streaming. Oh, I am streaming. Alright, cool. Cool. How's the audio? Cool. How's the audio? Cool. How's the audio? Cool. How's the audio? Ooh, let me not play that. Alright, so we streaming. That's pretty cool. I hope the audio is okay on your end and it's not echoing. But yeah, anyways, let's get into it. So binary search, just slide this over. The right side of my screen. Let me alter this. Oh, did I do something? Alright, so let me open up this binary search. What happened now? Alright, so let's go through this real quick because I honestly don't. Oh, wait. Let's put this in Markdown instead, not Swift. Alright, so let's just read through this. So binary search, an algorithm designed to locate a specific item within a sorted collection. Its power comes from having the portion of the data where target element. Okay, you have a defined search range, and I think the array has to be sorted too. Anyways, you find the middle element within this range. You compare the middle element to your target, and if they match, you found it. If the target is smaller, you discard the right half of the current range. If the target is larger, you discard the left half. That makes sense, and you repeat. Okay. So some rules. So this is non-negotiable. The array has to be sorted, which makes sense. It's primarily efficient element recognition. Return the index of target. Okay. Okay. So that's how you recognize some of the patterns. Finding boundaries and thresholds. This is a more advanced but very common interview application. I don't really know. Okay. Find the minimum and maximum value for which a property holds true. Smallest x that satisfies condition. Okay, I see. Okay. Alright, so let's just go through this code real quick. So the usual time complexity for binary search, O log of n, which makes sense because each step cuts the search space in half, and it's O of one space. Key idea is to define a search space, calculate the midpoint, compare the target with the value at mid, and adjust the search space, either move left or right. So this is the base primary search. Okay. This is like first occurrence type stuff. Okay, so basically the same thing, like exactly the same thing. Oh, the first occurrence, I see. Wait, how does this actually work? Because it says, trying to find the first occurrence of the number. Try to find earlier occurrence in the left half. How would you do that actually? Because if you're trying to find the first occurrence, then you get the midpoint, and you say if the midpoint equals a target, which is the first occurrence of that target, you set the first occurrence to mid, and you make the right equals. Oh, okay. So you just keep going down. That makes sense. Okay. Square root. 2. I'm not gonna lie. I don't understand what's going on here, but I think we'll get to it eventually. Okay, so I understand binary search. Key idea: you want to look for a target in a sorted array, or sorted collection. Start from the middle and see if that's your target. If the target, or if what you're looking for is greater than the target you're looking for, since it's sorted, you can decrease the right side since you know that what you're looking for is less than the target. Okay, I kind of get it. All right, so let's handle this question. Search a 2D matrix. Ooh, 2D matrix. Okay. I kind of forgot how to. I think I can remember how to handle 2D matrices in Swift. Okay, let's tackle this. 74. So search a 2D matrix. You are given an m times n integer matrix with the following two properties. Each row is sorted in non-decreasing order. Okay, I hate when you say that. So rows are sorted in increasing order. Why is this not working? Oh, Swift. Ooh. Rows are sorted in increased order. Okay, and the first integer of each row is greater than the last integer of the previous row. Okay, so first integer of each row is greater than the last integer of previous row. Let me just write that down so I remember. All right, so given an integer target, return true if target is in the matrix or false otherwise. You must write a solution log m times n. Okay, so if we must write this solution log, from what my understanding is, I have a pretty decent understanding of time complexity, I hope. So what I'm thinking is that we know binary search is log n, right? But we have m here, and I'm assuming m corresponds to the number of rows because it says you're given an m times n integer matrix, and that's usually rows and columns. So let me say rows times columns equals m times n. So what I'm thinking we do is that for each row, do we have to worry about, okay, we'll get to that. What I'm thinking we do in the plan is that for each row, we perform binary search on the row and return the target if it exists, right? Else, let's just return -1 since the target, oh, well, we're returning true. So we don't have to return a target. We can just return true if target exists, else false. And that would be O log of n because we're having the binary search log of n and then we're going m times m, so row times. But what I'm curious about is, do we have to we have to make sure that these numbers are in order. Let me see. M equals matrix length, n equals, okay. 1 is less than m, okay. Okay, because it could be negative. Okay, this is pretty straightforward, I believe. So how I'm going to do this simply is that for each row in the array, or for each row in the matrix, we need to perform binary search. So first, let's get the row. How do we get the row? We get the row by accessing 2D arrays. So if I have this matrix, or if I have this right here, I should know this. This should be like this for me. Whatever. If I just say, oh, matrix 0, that's okay. Come on now. All right. All right. So let's say for I in 0 less than matrix dot count. I believe that's in Swift, which is matrix dot count. Is matrix dot count the number of rows? 1, 2, 3. Yeah, number of rows. Var for, well, should it be var or let? Let's make it constant because we don't want to change it. So let current array equal matrix I. So now we should have the first row in the matrix. Then we perform binary search. Let me say return false or whatever. So now we perform binary search. So we say var I, or let me say start equals 0, var n equals current array dot count, which is the end of the array, -1, the end position. While start is less than or equal to end, what do? Now we need to calculate the midpoint. So we say var mid equals start plus end divided by 2. I'll give you the midpoint. Because if this is, let's say here, let me make this an int so it rounds down. So if this is here, if this is a start at 0 and this is the end at 0, 1, 2, 3, it's going to say 3 divided by 2. It's going to default to 1. All right, so let's do that. Var mid equals int start plus end divided by 2. Okay. Then we can say if current array mid equals the target, then we can return true. Else, if if current array mid is greater than target, what do you mean? What do we do? That means we have to, if it's greater than a target, then we have to decrease the right side, because that means we got a mid that's larger than the target. Oops, sorry. So we say end minus equal 1, else start plus or equal 1. Okay, so let me run through this on paper just so I'm sure. That's my notebook right here. Can you guys see? Let me make sure you can. Okay, you won't see the paper for now, but it's just a blank piece. I'm just sketching out the floor. So let's take this first grid here. Let me write the name of the problem. Search 2D matrix. My handwriting is so bad. This is my handwriting, if you can see. I don't know if you can see, but it's so bad. Okay, anyways. So for I and 0, which is matrix I count, so we're at I equals 0, we say current array equals matrix 0. So we get matrix 0, which is 1, 3, 5, 7, right? While start is less than or equal to end. So start is at 0, okay, end is at current array. We get the midpoint, which is 3 plus 0 divided by 2, which, since it's integer conversion, it'll be 1. I hope so. Yeah, it'll be 1. And then we get, if current array mid equals target, current array 1, 0, 1 equals target, which is 3, we return true. And we get the answer for this one. How about this one? To number 13. How would this work? So this is pretty simple, actually, I think. Hopefully we get it right when I submit, because we're just doing binary search for each array, which is a log of m. Should be, at least. So let's run it, see if we get the right answer. Does array have to, wait, we do have to check for empty arrays? No, it'll always be element. Let's submit. Yes! 0 milliseconds. I beat 100%, which is so funny. Wow, that doesn't really mean like that, but like, yeah, this is the log of n, and we can tell. So yeah, that's cool. So now what I do when I solve a problem where I can't complete it, I just look at the other solution to see how you could have done this. So I did it this way. Let's see LEET-CODE. LEET-CODE did it this way. LEET-CODE. Okay, do we have one in Swift? So it did one by brute force. Okay, so this is the brute force solution, O of m times n. Let's see, so you, for each row and for each column, you check if, oh, brute force. Okay, so that's just iterating through the matrix and seeing target matches. Then there's a staircase search. I've never heard of this. O of m plus n. Staircase search. So you let m equals matrix dot count. Okay. Let n equals the first array dot count. Okay. R equals 0, C equals n minus 1. While R is less than m. Okay, well, I'm not gonna lie, hold on. I need to paste this into, see, the thing I don't really like about the LEET-CODE page, like, his solutions are amazing, but the fact that his variables are just really not descriptive enough for me, I kind of get confused. So let me put this in Gemini and just say, hey, remake this function, but use better variable names. This is staircase pattern. I spelled that so wrong. All right, first, actually, let me do something real quick. Let me copy my solution in here. Let me, here it is. Let me just say binary search solutions. This was, what number was this? This was 74. Where is the LEET-CODE? 74, search a 2D matrix. This was surprisingly not that bad. I thought it was going to be terribly hard. Okay, whatever. So, where's the, okay, so let's copy this. Ooh, maybe I shouldn't do it. I don't like using spaces. 74, search 2D matrix dot swift. Okay, so this was my solution. Let's copy that. My solution. my solution, and these are the others. All right, so we have the staircase pattern, which is what LEET-CODE did. Let's take a look at that real quick. Okay, so you had the search matrix, you had the number of rows. So get the number of rows in the matrix. If there are no rows, the matrix is empty, so the target can't be found. Makes sense? Wait. Can there be no rows in the solution? Did I miss that? If there are no rows, then there has to be 1, because 1 is less than or equal to m. M is the rows. It's always going to be m solution, so this is not really needed. So anyways, what we say num_cols equals matrix.count. Okay, so we get the number of columns, and we get the number of rows. Makes sense. We get the current row, get the current column, and say continue searching as long as current row is less than num's row, and current row. I kind of get that. It's just a weird way of doing it. Like, something's not mathing in my brain. I'll have to draw it out, which I don't really want to do right now, but maybe I'll do it later. Let's look at the other ones. Okay, is there like a solution? Why does mine seem so easy compared to what these guys did? Wait, is this the right question? How did I do mine so... Is this, what complexity is this? This is a log of n, right? Let me check to make sure. That is a log of n, no? Oh, wait. No, yeah. What is it? Okay, space is O of 1. What's my space complexity? Assuming current array holds a reference, the total space complexity is O of 1. No, sorry, time complexity, I know that. Yeah, OM log of n. That's what I did. Nice. But like, what did he do here? He must not, let me see in Python. Python's always, okay, this is kind of, why he's using the modulus operator. What rows equals what columns, okay. So is my way not efficient? Left 0, right is rows times cols minus 1, okay, get the number of elements. Oh, that's a pretty smart way. So he gets the midpoint, which is left plus arm minus left. I need to put this in simple language too. Hold on. All right, so search matrix. Okay, so initialize binary search range. You have the low index and you have the high index, which is num times row, nums rows times. Okay, calculate the middle index using low index plus high index minus low index, which prevents overflow. Okay. I'm gonna have to draw this out. My brain, like when it comes to 2D problems or 3D arrays, I literally cannot think. Like, I have to draw it out. Otherwise, like, it's gone in my head. So I'll do that later. But since we got it right, we'll move on. Let me just do this problem dissection here of the such a 2D matrix. I'll show you what I mean in a second, which I'll handle. So I just like paste the problem into Gemini, and it gives me this like how an interviewer would solve this issue or solve this problem. I'm sure it'll do it like LEET-CODE did it, but let's see what it says. Let's put this above. So this is what it said here. It says from now on, put it in Swift. Yeah, I forgot. I was using Python for a while, but like I don't know why I finally decided. I don't know why I was kind of like, oh, well, I'm trying to become an iOS engineer, so I really should be using Swift and not Python. Ultimately, the language doesn't matter, but I feel like if a company is going to interview me or whatever, then they're going to expect some Swift proficiency. So I might as well just do it in Swift instead of Python just so I can get better at it. So I did mine wrong. This was the right way to do it. I need to understand this. So the moment I see sorted data structure and O log event time complexity, my brain immediately screams binary search. Yes. Yes. Okay. Thought process. Search for a target in 2D matrix. Rows are sorted. First element of each row is greater than the last of previous. This is crucial. This it means that implies 7 is less than 10. Okay. Is that what it implies? Yeah. Okay. So matrix row call is always greater than matrix row minus 1 and equal. So matrix row call. So let's say this is always greater than the same column, but row minus 1. Yeah, that makes sense. Okay. Effectively, the entire matrix is sorted if read row by row. But how do I apply binary search? Why is mine bad? Hold on. Treat the matrix as a 1D array of size m times n. A 1D index mid can be converted back to 2D coordinates. Row equals mid divided by n, because that makes sense. But the column is different. The column has to be modulus. Oh, okay. So the row, to get the mid row is whatever. You have 3 rows. What am I saying right now? Where is it? Row equals mid divided by n. Okay. Column equals mid mod n. Okay, let's see the algorithm breakdown. So get dimensions, rows equals matrix count. Define search space. Okay. Okay, so we get the midpoint. Do we get the midpoint? Oh, we get the midpoint of everything. So what would be the midpoint of, so midpoint of 10 will be 5, and then you're saying row, if there's 10 rows, you say row equals 5 divided by the number of columns. Okay, so let's take a look at this. So there's how many numbers? There's 12 numbers here. Oops, sorry guys. 12 numbers there, meaning that with 12 numbers, my brain is going because I'm thinking about 2D matrices. The mid will be 6 to start off. Would it be? Because you're saying 0 plus 12 minus 12 divided by 2, 6. And you're saying row equals 6 divided by the number of cols, which is 4, which integer division should yield. What would integer division yield? It wouldn't be. Okay, so mid mod cols would be 2, so column 2. But row divided by mid, and the division would be that 0. That's confusing to me. I don't like that. Where's this Python walkthrough thing? What's it called? What's this? This is a website where you can paste code and it like walks you through it. Let me just say Python walkthrough code compiler. Here it is. Oh, I did not have Swift. God damn it. Okay, thanks. Give me Python. Ooh, this is very small. Okay, let me just tell it to give me the code in Python. What the heck is this? Let me paste this. Okay, I gotta move to the next problem. It's been, what, 30 minutes and I'm on one problem. So I gotta hurry up. Oh my god, the comments. Let's get rid of this. Should be okay. Give me this. Let me just give me the matrices. Okay. Then let me just call search matrix. That's not what I wanted to do. Oh, this is so annoying. I hate how it's all the way on the left side. What is this format? Can I? Okay, search matrix. Matrix target. Don't give me errors, please. Okay, here we go. Let's widen this. Okay, so you start from here. Get the matrix, pass it in. Yada yada yada. Okay, so we have rows equals 3. Okay, columns equals 4. Low is 0, high is 11, not 12. So while low is less than or equal to high, we calculate the midpoint. So the mid would be 5, which makes sense. The rows integer division, so it would be 1 because 5 integer division by 4 is just 1. And that's 1 too. That confuses me, integer division. I need to research how that works again. I'm so out of it. I haven't done this in such a long time. But okay, let me just see how integer division. Remind me how integer division works in Swift and Python. Okay. So it's like the modulus. That's what I'm confused. Okay, I don't understand what he did entirely, but I think I get the idea. He's basically just doing binary search, but with all the numbers. So I like actually broke it down by doing row by row, but what LEET-CODE did was didn't break it down row by row. It just used the entire grid and just found a midpoint over and over again. That makes sense. Okay, let's take a look at the next problem. Koko eating bananas. This can't be good. I think this might be my last problem, not gonna lie, because that 2D matrix thing just blew up my brain. So I think I'm gonna... Okay, anyways. So Koko loves to eat bananas. There are n piles of bananas. The ith pile has piles I bananas. The guards have gone and will come back in H hours. Okay, so n piles of bananas. Ith pile has piles I bananas. The guards have gone and will come back in H hours. Okay. Koko can decide her bananas per hour. Eating speed of K. Each hour she chooses some pile of bananas and eats K bananas from the pile. If the pile has less than K bananas, she eats all of them instead and will not eat any more bananas during this hour. Coco exceeds slowly but still wants to finish. Return the minimum integer k such that she can eat all the bananas within 8 hours. I don't get it. I'm gonna have to reread this. Alright, let's write some things down. So, whoops, what just happened? Am I still streaming? Okay, so, yikes, that's not good. Alright, so we have n piles of bananas. Okay, that's simple to understand. We say in piles array, the ith pile has piles I bananas. That makes sense. So each element in piles represents a number of piles. The guards are gone, so guards will come back in H hours. Okay, so Koko cannot eat while guards are there. She can eat while guards are gone. Koko can decide her bananas per hour, eating speed of K. Okay, so Koko decides how many bananas she eats per H at speed K. Each hour she chooses some pile of bananas and eats K bananas from that pile. Okay. If the pile has less than K bananas, if the pile has less than K bananas, she eats all of them and stops eating bananas within H. And we have to return, so we're returning the minimum integer K such that she can eat all bananas within H hours. Wait, what's K then? Return the minimum integer K such that she can eat them. I don't get it. Okay, let's take a look at the example. So hours is 8, so K is the minimum integer such that she can eat all bananas within 8 hours. So does it mean she can eat 4? I don't get this problem. It's not math in my head. LEET-CODE this. I hate LEET-CODE. Okay. Koko loves to eat bananas. There are n piles of bananas. I'm tired. I don't even want bananas no more. I'm about to start protesting against bananas. I'm done. I'm not eating bananas after this. The guards have gone and will come back in 8 hours. So each hour, she eats K bananas from a pile of her choice. If the pile has less than K bananas, she eats all of them instead. So every hour, she chooses a pile and eats. Okay, hold on. I'm going to say something, and I'm not really thinking about it, but I'm just going to say it anyways. We know we're dealing with binary search here, because obviously that's a pattern. Let's see. And it's saying that if a pile has less than K bananas, she eats all of them instead and will not eat any more bananas during this hour. And we have to return a minimum integer such that she can eat all the bananas within H hours. So the number of bananas is the sum of the piles. And we want to return a minimum integer K, which is, why do you use K for everything? K is speed, K is, hold on, Koko can decide her bananas per hour eating speed. Oh, I read that wrong. I thought, okay, Coco can decide her bananas per hour eating speed of K. Each hour she chooses some pile of bananas and eats K bananas. So K is the amount of bananas she eats. So we're returning the minimum integer K such that she can eat all the bananas within each hour. I hate the wording. Maybe I'm stupid, but I don't like the wording here. They use K too much. If the pile has less than K bananas, she eats all of them instead. I will not eat any more bananas during this hour. It's so annoying because I have an idea, but once I need to understand what K is. Return the minimum integer K such that she can eat all the bananas within 8 hours. But what is K? If the pile has less than K bananas, she eats all of them instead and will not be any. Okay, so K is the number of bananas she eats in a pile. Oh, no. We have a pile. Someone commented in my chat box. What do they say? Cheap viewers. Oh, thanks. Appreciate you. How do I like? Oh. Okay, whatever. This problem's getting on my nerves. I just need to understand what K is. I'm not understanding that. What I know is that we have N piles. Each pile has piles I bananas. So we have 3 bananas here, 6 bananas here, 7 bananas there, 11 bananas there. Okay, and we have 27 bananas in total. She can decide her bananas per hour eating speed of K. What is K? Where did K come in? I'm returning a minimum integer such that she can eat all the bananas. So am I returning the minimum number of bananas she can eat within 8 hours? Because in 8 hours here, what does a 4 represent here? But in 8 hours, she can eat 3 of these, 6 of these. This is not a good. Hold on, let me look at the discussion. I don't want to find a solution, but. Oh my, I'm just dumb. No one. Dude, how long have I been trying to understand this? I need to understand what K is. That's my only issue here. Coco can decide her bananas per hour eating speed of K. So K is not the speed, it's deciding her bananas per hour eating speed of K. Each hour she chooses some pile of bananas and eats K bananas from that pile. So whatever her eating speed is, if it's K. So let's say her eating speed is 4. Each hour she chooses some pile of bananas and eats 4 bananas of that pile. If the pile has less than K bananas, she eats all of them and will not eat any more bananas during this hour. Okay, so let's say K is 4. This is less than, so we eat 3 hours. We have 7 hours left to finish this whole thing. Then we have 6, right? and we have, and K is 4. So she eats 4 bananas per hour. So we're still here at 4. She eats another 4. We have 2 more. Okay, so from my understanding now is that K represents the number of bananas Coco will eat per hour, and we have to find the minimum number of bananas Coco can eat such that she can eat the entire thing. Such that she can eat the entire thing under H hours. Okay. So how can we do this? BFK represents the number of bananas Coco will eat per hour, and we have to find the minimum number of bananas Coco can eat such that she can eat the entire thing under H hours. So there's really no is there a maximum? 10 to the ninth is the maximum number of bananas this girl, Coco, can eat. Or, sorry, this gorilla can eat. Um, so the minimum banana she can eat. Can H be 0? No, H must be 1. So the minimum number she can eat is 1, right? She always eat 1 banana. So if I start at the first section, wait, I need to walk through this in an example first before I try to solve it, because I'm not understanding how you got 4 here. So let's say 4, let's say 4 is the minimum integer. You start from here, 3 is less than 4, so you eat all 3, right? And represents the number of bananas. Wait, no, K is not the number of bananas she's gonna eat. K is not the number of bananas. K is not the number of bananas Coco can eat. Oh my god, I got no one in my chat to help me, bro. It's just me. Okay. Yikes. This is not good. I still don't understand K. Okay, so example 2, it's 30 because Coco can eat 30 bananas. That's the first one, because since you start from the first element, you already eat 30 bananas, right? But she can pick from any pile. So what if we sorted that? What if we sorted example? No, let's just do example 1. So you have 4 here. It's sorted already. We can pick from any pile to eat. Okay, I'm gonna look at the solution because I'm not understanding this right now. Let me watch LEET-CODE's videos. Where's the... Oh, it does this. Sorry. Warning. Oh my god. Let me just open this on YouTube.
This may be the last ad you ever see. Because with the free ad block extension from...
Hey everyone, welcome back, and let's write some more LEET-CODE today. So today let's solve Coco eating bananas. But before we do, I just want to say that if you do have any requested problems, you can feel free to leave those in the comments. I do have a large backlog of requested problems that I'm working through, so it may take some time for me to get there, but you can feel free to request at any time. And if you find this video helpful, don't forget to leave a like and subscribe for more videos. So this is a pretty interesting problem because there is a brute force solution that we can arrive at, and that brute force solution can easily be transitioned into a binary search solution, which is the optimal solution for this problem. So we're going to be working our way from the brute force to that binary search solution. So Coco loves eating bananas, and we have n piles of bananas given to us in a piles input array. We're also given a second parameter, h, which is the number of hours that we have in order to eat all of the bananas. So we have to eat them within h hours. And so Coco has a certain eating speed where she can eat a certain number of bananas per hour, and that variable happens to be k, and k is not an input variable. That's what we're trying to determine as the solution for this problem. Each hour, she can only choose one pile of bananas and eat k bananas from that pile. So that's what we're trying to determine, that k value. If the pile has less than k bananas, she'll eat all of the bananas, but she's not going to eat any extra bananas from a different pile. So what we're saying here is Coco can only eat at most one entire pile of bananas in a given hour. So what does that tell us? Already we're given some key information. Let's say we're given a certain number of piles, right? So basically the length of p, h must be greater than or equal to the length of p. Why is that? Because let's say we have 5 piles, right? So let's say we had 5 piles, and let's say this is what the piles look like. The values aren't too important, right? 1, 1, 2, 2, 3. And let's say we had h equals 4 hours. Well, let's say k equals some really big number, like 3, right? Basically the max of this input array. Okay, Coco ate this entire pile, Coco ate this entire pile, this entire pile, and this entire pile, because she could only eat 4 piles because we only have 4 hours, right? Coco can only eat 1 pile per hour. So if she ate all 4 piles over here, we'd still have 1 left over. That's why they guarantee us that h is always going to be greater than or equal to the number of piles. So the minimum in this problem, given this input array, h, the minimum it could possibly be is going to be 5. And I sort of wrote over it, but the last important thing that they tell us in the problem is we want to determine that eating speed k that Coco is going to eat at, but we want to know the minimum integer k, the minimum eating speed of Coco, that she could eat all of the piles in exactly 5 hours, or exactly whatever that time interval, that number of hours happens to be. So let's take a look at this example. They give us an input array of 4 piles, and they give us 8 hours to eat all 4 of those piles. What's the minimum k, the minimum eating speed that Coco could use to eat all of these piles in at most 8 hours? So we have to eat all the piles in 8 hours or less. Well, the brute force would be to start at 1, right? Because Coco could try k equals 1, right? Can we eat all piles in 8 hours then? Well, it will take us 3 hours to eat the first pile, right? 3 divided by 1, which is our K, right? 3 divided by 1 is going to be 3 hours to eat this first pile. And to eat the second pile is going to be even more. That's going to be 6 hours, right? 6 divided by 1, 6 hours. So far we already have 9 hours, and we haven't even eaten the entire number of piles. So therefore, K equals 1 is not going to work. And we could just continue this brute force approach, right? Now try K equals 2, right? And then do the exact same computation with K equals 2. Now, my question to you is we know that the minimum possible solution would be K equals 1, right? K can't be 0 because that would mean we're not eating any pile. So the minimum is 1. What's the maximum that K could possibly be given this input array and given this number of hours? Well, remember, the number of hours is always going to be greater than or equal to the number of piles. So in the worst case, K would basically be the max number that happens to be in our piles. For example, if K equals 11, right, that means we're able to eat the max pile in exactly 1 hour, right? And if we can eat the max pile in 1 hour.
My brain hurts. So I'm just gonna, let me just get rid of this epilepsy. I'm just gonna start this and then attempt it some other time. Let's look at the solution so I see. My brain hurts, man. Okay, total time is less than or equal to H. Res equals K. R equals K minus 1. But hold on. How is K the midpoint? Yeah, I'm gonna watch a video. I kind of get a okay idea, but I'll watch a video later on. Okay, so I think we just could continue on tomorrow. I cannot do this, or maybe I'll start up later again, but yeah. See you later.